Okay, so last time we were talking about equivalence of matrices, and the definition was that A is equivalent to B if B is x A y, where x and y are invertible matrices. And even though I did not say anything, we were assuming that these matrices have entries in field like real numbers or complex numbers or rational numbers, whatever you like. But today I want to talk a little bit about polynomials. We look at polynomials with real or complex or rational coefficients. So, something like 4x squared plus 3 by 2x plus 5, that is a quadratic polynomial. The polynomial has something called degree. This is just what is this? The degree of this? It is 2. It is the highest power of x which has a non-zero coefficient. And this degree plays a very important role in the algebra of polynomials. It plays the same role that absolute value plays in integers. Namely, you have something called the division algorithm. This is something that Euclid talked about in a textbook he wrote more than 2000 years ago. He said that if you have two numbers, then we do this in I do not know, third or fourth standard maybe. If you have two numbers, then you can find a quotient and a remainder. So, you can write if you have two numbers, say x and y, then you can write x as qy plus r, where this r is between 0 and y, but strictly less than y. Okay, so this is something we all know, the division algorithm. And here maybe we should say absolute value of y could be negative, it still works. Okay, if y is negative, you could just do it with the positive y and then put minus in front of it, and it has more or less the same effect. Now, this algorithm also works for polynomials. Only thing is that this degree has this condition has to be replaced by degree of r less than degree of y. It is also possible that r is 0, okay, in which case I do not know, maybe we could call its degree 0, or we could, I do not know what.
This is a matter of notation.
Yeah.
That's now you can write f of x is equal to.
Oh yeah, good point. So maybe I will change this to t.
Okay, fine.
Yeah. So, I will be looking at polynomials in t, otherwise there will be too much confusion if x is a polynomial and x is also a variable. Thank you. So that's the division algorithm. And how do you do this? It's the same, long division. Suppose I want to divide this by x minus 5, then I can sort of see how many times t minus 5, I can see how many times this goes into this. It goes in 4t times, and then I get 4t squared minus 5t, and then I subtract, and you know this, right? It's just the same way that we do division for integers, we can do division for polynomials. The only thing is that degree plays the role of absolute value. And there is another thing we do with integers, which is find GCD of two integers. So, GCD of two integers, what we know is that if you take two integers, then there is a unique third integer which divides both of them, and it also anything else which divides both of them is divisible by this. Okay, so if you have two integers x and y, then let us say g is GCD of x and y, then what is the definition of this? One way of thinking about is g divides x, g divides y, and whenever say h divides x and h divides y, h also divides g. Okay, so if anything divides x and y, it must divide g, and g divides x and g divides y. The same, and how do we compute this? We use again an algorithm from Euclid's textbook, which is that we start with x and y, then we take out the remainder, and then we take this remainder and x. I guess we take out this remainder and y, and then we take out the remainder from that, and we keep doing that until no remainder is left, and then we get the GCD of these two. So, these are things we have learned in some point in school, but the important thing is now that we can do the same thing for polynomials. So, I just want you to remember from this discussion is that if we take two polynomials, now there is a slight issue here. You can take a polynomial and multiply it by some scalar. So, I can take this polynomial and divide it by 4, and I get another polynomial t squared plus 3 by 8t plus 5 by 4. And this is divisible by this, and this is divisible by this, because this is 4 times this and this is 1/4 times this. Okay, 1/4 is allowed here because it is a polynomial. Like there we were using integers, so all when you divide it, any integer was allowed. But here any element of the field is a unit, it has an inverse. In the integers, the only units are 1 and -1. Okay, -1 also has an inverse, -1 times -1 is +1. In polynomials, there are many units. So, any constant polynomial is a unit. Okay, so if you have a constant polynomial a, then a inverse is also a constant polynomial, and that product is the constant polynomial 1. So there are lots of polynomials which have multiplicative inverses. They are the constant polynomials or the polynomials of degree 0, except for 0, of course, the polynomial which is identically 0. So, so if you have two polynomials, then you can talk about the GCD, but just to make it unique, you can say that it is monic. G has leading coefficient equal to 1. Otherwise, there are too many GCDs. Okay, and the algorithm for computing this is the same as this. Okay. Okay, so now with just this little background, I want to talk about the equivalence problem for matrices whose entries are polynomials. So you could look at a matrix like this, something like 1 minus x, t, 1. Okay, so let's say, okay, so yeah, we could look at a matrix like this. This is a matrix, and it's a matrix whose entries are polynomials. Okay, what is the determinant of this matrix? You can use the same formula to calculate it. It's 1 minus t times 1 plus t minus t squared. So, it's 1 minus 2 times t squared. And we can try to write down the inverse of this matrix. So, again it's the same method. What you do is you compute the determinant, you take 1 over determinant, and then you replace each entry by minus 1 to the power I plus j, which is the ijth entry, you replace by minus 1 to the power I plus j times the minor corresponding to j comma I, right. So this one will be replaced by this minor, this one will be replaced by this minor, this one will be replaced by the negative of this minor, of this minor, and this one will be replaced by the negative of this. So this is, if this is A, then this is A inverse. Now this A inverse is not a matrix with polynomial entries, because if you write it down as a, if you bring this inside, you get 1 plus t over 1 minus 2t minus t over 1 minus 2t minus t over 1 minus 2t and 1 minus t over 1 minus 2t. So this is not at all a matrix of polynomials, it is a matrix of rational functions. Okay. These are not polynomials. So we can't invert every matrix whose determinant is non-zero and get a matrix whose entries are polynomials. We may end up with a matrix whose entries are rational functions, because this determinant comes in the denominator and this is not a field. So, after dividing you are no longer in this thing. But suppose instead of t I had minus t here, then this would become plus t squared and the determinant would become 1 and the inverse would just be this. So if the determinant is, even if the determinant was 2, that would not be a problem. For example, if I had 2 minus 2t, 2t, then the determinant would become 2 times this and it would become 2, and here I would have 1 over 2, but that is fine because this 2 would go in and these would still be polynomials, right. So so long as the determinant is a constant, you can invert the matrix, just using the same old rule of replacing each entry by the minor of the of replacing the ijth entry by the minor of the jith entry with the sign minus 1 raised to I by j and dividing by the determinant. So so a matrix, a polynomial matrix is invertible or non-singular if and only if its determinant is constant. I mean, you have to be a little careful here. When I say invertible, I mean its inverse is also a matrix with polynomial entries. If you don't care about whether the inverse has polynomial entries or rational entries, you don't, it's fine. If the determinant is non-zero, it will still be invertible. But because we want the inverse also to have polynomial entries, the determinant would have to be 1. Okay. Now you will be wondering why I am doing all these things. Let's just come to, let me just say that this will be related to the problem that I introduced at the end of the previous lecture, namely classifying matrices up to similarity, where we had another definition: A is similar to B if and only if B is A excellence for some invertible x. So just keeping that in mind, these are the correct definitions from that point of view. So now if we take this definition of equivalence, then what we get is two polynomial matrices are equivalent if B is x a y, where x and y are invertible polynomial matrices. So it means that the determinant of x and the determinant of y are constants. That's the thing. So now what we want to do is study equivalence of polynomial matrices. What we have is x is equivalent to y if and only A is equivalent to B, if and only if B is x a y, where determinant of x, determinant of y are constant polynomials. So, this is something which is invertible. When I put plus instead of minus here, it is not invertible. Okay. So, now what we want to do is try to find canonical forms for such things. So, we will do whatever we did last time, we will use row and column operations. So, suppose I take this matrix 1, 1, 1, 1 and then here alpha and 1, 1, 1, 1. Can you tell me, is this matrix, so here alpha is a polynomial. Okay. So, is this matrix invertible? It is invertible if and only if alpha is constant non-zero, right. If alpha is of degree greater than, if alpha is non-constant, then alpha inverse becomes a proper rational function. So, this is invertible only if alpha is constant. So, alpha constant. And so, that we are still allowed to do this operation Ri goes to alpha Ri, Ci goes to alpha Ci, provided alpha is a constant. Now, let us look at the other operation we had 1, 1, 1, 1, 1 and then we had alpha somewhere in the ith row and jth column. What about this matrix? When is this invertible? What is its determinant? 1. So, it is always invertible. Alpha can be any polynomial. And so, we are allowed to do Ri goes to Ri plus alpha Rj, Cj goes to Cj plus alpha Ci for alpha any polynomial. And the last operation was interchanging two rows and columns, and that anyway was a matrix of zeros and ones. So, its determinant does not depend, is going to be constant because all its entries are constant. So, we are also allowed to interchange Ri and Rj and Ci and Cj. So, we are allowed to do all these operations and we are allowed to try to bring our matrix, and our goal is to try to bring our matrix to some canonical form. In this case, the canonical form is called the Smith canonical form. So, So, it is very much like the previous one. Earlier we had 1, 1, 1, 1 and then zeros everywhere else. But here you may not be able to make everything 1. For example, if you just have a 1 by 1 matrix, you can't do anything to it. At most what you can do is you can multiply its only entry and make it a monic polynomial. But if this is like 2t plus 1, you can't really make it 1 because you can't divide by 2t plus 1, you will be right, that is not an invertible thing. So there is nothing much you can do except make it a monic polynomial. So what you can, so you can't expect to get 1 1 1 1 here, but what you can do is you can get some polynomials here f1, f2, fr, and then the rest will be 0. And you can do it somewhat cleverly in such a way that f1 divides f2, f2 divides f3 divides fr. So, a Smith canonical form is a matrix which is of this shape. And what I am going to show you is that using these row and column operations, any polynomial matrix can be reduced to Smith canonical form. And we will also see that the Smith canonical form is a unique one. That means no two of these different Smith canonical forms can be the same. I also want to assume that these polynomials are monic because of this. Because I can always multiply them by some constant. So if I want it to be unique, I need monic. Okay. Let's see how to do this. This is slightly trickier, but the idea is almost exactly the same. So there's an algorithm I'll give you, which you can easily turn into a computer program if you wish. And it's very much like the previous time, where we just focused on the first row and first column, and then try to get it into a nice form. So here's the main step of the algorithm. Yeah, so the main step of the algorithm is this. So you start with a matrix A11, A12, A1M, I guess this is N and this is M. Okay, and then you have more stuff here. I'll call this A prime. A. Oh yeah, A N. Oh, M1. Yeah, and then here you have some remaining stuff which I'll call A prime. And now I'm going to show you an algorithm which will do one of two things. It will either then, by performing elementary row and column operations, A can be reduced to either, so the good case is B, where B is of the form B11 0 0 0 0 0 0 0 B prime, and B11 divides. Now these, remember, these are all polynomials. Every entry of B prime. This is the good case, because if we can do this, then we can apply the same algorithm to this B prime and hopefully do that and then keep doing it. Okay, so, and then there's the bad case, but we'll see how to manage the bad case later. So the bad case is C11, C12, C1n, C21. There's really nothing much going on, except that the degree of C11 is strictly less than the degree of A11. Now see why this bad case is not so bad. You start with this will have some fixed degree, maybe the degree is 5000, okay. Then each time you perform this algorithm, which I am going to describe, I haven't yet told you, the degree of this term will go down. How many times can it go down? At most 5000 times, right? Once it reaches 0, then it will of course divide every entry of B, because constants, they divide any polynomial. So after finite number of steps, you will be forced to reach here, and so you can proceed. So what I am going to do is describe an algorithm which, by performing elementary row and column operations, can be reduced to one of these two. So here's the algorithm. It's again somewhat similar to the previous thing, but it will use this Euclidean division algorithm. It's just a more careful thing of doing the previous thing, but much more carefully. So we'll consider cases. So I just wrote down the cases in my notebook. It's good to organize them carefully. So case 1 is that there exists, suppose A1 does not divide one of these elements. Okay, this is a bit like saying that A1 is 0 in the previous algorithm. So suppose A11 does not divide one of this. So A11 does not divide A1j for some j greater than 1. Then you can use the Euclidean algorithm. Then A1j can be written as q times A11 plus r, and this degree of r is less than the degree of A11. So what you do is, now you take this column Cj and change it. So here I have got this element A1j, and what I can do is I can take this column Cj and subtract from it q times the first column. Then what will I get in the 1/1th position? No, not in the 1/1th position, in the 1jth position. I'll get this thing minus q times this thing, because this is the first column entry. Right? I'm taking this column and subtracting from it q times this column. So what will I get? This will become r, and this r has small degree. Now the next step what I can do is I can interchange r at the first column and the rth column. And then I end up with this case. Is of type C here. And the same kind of thing you can do in case 2, where A11 does not divide AI1 for some I greater than 1. So again what you can do is you can write the I1 in terms of A11 quotient and remainder thing, and then you will do row operations and you will interchange rows. And again you will be able to bring that smaller remainder up and do the same thing. So it's exactly the same. Let's not spend too much time on that. And so now what is the remaining case? The remaining case is that A11 divides all these elements and all these elements. Okay. But that means that if I have any element here, A1j, then A1j is some multiple of A11. So by subtracting an appropriate multiple of A11, I can make all these entries 0, and I can also make all these entries 0. But there's still one more thing. This A11 may not divide every entry of A prime. Now, so there's some entry in A prime which A11 does not divide, but then what I can do is, let me just write it down a little bit. So case 3, A11 divides AI1 for all I, and A11 divides A1j for all j. Then you can get this form A11 0 0 0 0 0 0 by doing those row addition things, and here you will still have some matrix A double prime. You would have changed the original thing that you had. Now there are two possibilities. If A11 divides all the entries of A double prime, then we are done. But if it doesn't, then there is some entry here which it does not divide. So, some entry here. Then what you do is you just take the first row and add to it this row. Then you can bring this star up to the first row. And then you are back in case 1. And then you apply the method of case 1 to reduce the degree further. Okay, so it may take a lot of steps. I am not even going to ask you to try to estimate the number of steps, but I think that is a very interesting problem. So if you really are looking for something interesting to do, try to estimate the number of steps it will take. But as pure mathematicians, all we care about at this point is that in a finite number of steps, you will have achieved this kind of matrix. Many times you may have to go through this, but finally you will get this. And then inductively, now you will work only with this B prime, and you will be able to do the same thing. The only thing you have to check is that B11 divides every entry of B prime, then no matter what row and column operations you use, that fact does not change. B11 will continue to divide every entry of the transformed matrices B prime. Okay, and that is because if B11 divides all the entries, even if you add, so if something divides two numbers, if you add those numbers, it will still divide their sum, and it will divide their product and so on. So it will not change, and so what you will get eventually is this Smith canonical form by repeating this step with B prime. Okay, this is a little more complicated than the case when we had just matrices with entries, complex numbers or real numbers. We have polynomial entries, and we use somehow these nice properties of polynomials, Euclidean, this remainder, the division algorithm. We did not use GCD yet, that will come in the next step when I want to show that this form is unique. So, I want to show that this form is unique, namely that if I have two different matrices in Smith form, then they cannot be equivalent. And why is that? So, last time what did we do? We used rank. We said that if two matrices are in the canonical form, then if two matrices are equivalent, then they have the same rank. And but then those two different, if we had two different canonical forms, they clearly have different ranks. The rank of the canonical form is just the number of ones that you have in it. So here it's not quite that simple, but it's something very similar. And this is where we'll use GCD. So yeah. So let us just look at, for example, the GCD of all the entries of a matrix. So I have a matrix A, and you can take GCD not just of two things, but of any number of polynomials or integers, right? You can define it in the same way. It's a common divisor of, it divides all those numbers, and if anything else divides all those numbers, that divides this GCD. So in the same way, if you have any finite collection of polynomials, they have a GCD. So your matrix A, you can say GCD A is the GCD of entries of A. Okay. Now suppose I look at A times X times A times Y, and I want to look at GCD of this. So what can you say about an entry of X times A times Y? Let me write down a formula for a typical entry of this. A typical entry of this is Xi k a k l x l j summation k and l, right? Sorry, y l j. That's a typical entry of this. Now, the important thing to note is that this entry is, we can write it like this. Okay, so these are polynomials and this is also a polynomial. So, if something divides AKL, it also divides this product and therefore, it also divides this entire sum. So, if something divides AKL, it divides every entry of, if something divides every entry of A, it divides every entry of XAY. Okay, and this implies that GCD of A divides the GCD of XAY. Because the GCD is what? It's in some sense it's the greatest among all the divisors of all these numbers. And if the set of numbers which divide all these things are the same, so everything that divides the entries of this also divides the entries of this, then this will have more divisors than this. So, the GCD of this will divide this. But it also works the other way because x and y are invertible. So, I can write A equals x inverse times XAY times y inverse, and these are also polynomial. So, what I have is this again divides GCD of A. So, GCD of A divides GCD of XAY and GCD of XAY divides GCD of A. So, this means that GCD of A is the same as the GCD of XAY. So, the GCD of the entries does not change under equivalence. So, what does this tell us about our Smith form? What is the GCD of all these guys? Zero, everything divides 0, right? So, we will disregard the zeros. The GCD of 5 and 0 according to my definition is 5 because anything divides 0. So we can ignore the zeros, they won't contribute. So, basically it is the GCD of F1, F2 up to Fr. So, what is it? It is F1 because F1 divides F2, F3, Fr, and so F1 is the GCD of all these. So, what we see is that if two matrices, two Smith forms are equivalent, then the F1 must be the same for both of them. Okay, so at least the F1 part is unique. Now, what about the F2, F3 and Fr and so on? So, now this becomes a little more, one has to be a little more clever about this. Instead of looking at the GCD of A, let us look at the GCD of 2 by 2 minors of A. So, I will call GCD 2 of A. This is defined to be the GCD of all 2 by 2 minors of A. Let us see, why will this help us? What is the GCD of all 2 by 2 minors of this matrix? No, F1 squared is why? F1 squared is not even a minor here, right? What are the minors? Most of them are 0. Otherwise, you have to take two of these guys and multiply them, but two distinct ones, right? So, you have to take Fi, Fj where I is not equal to j. So, it is the GCD of Fi, Fj where I is, let us say, less than j. It is the GCD of all these things. So, it is the GCD of F1, F2, F1, F3, F1, F4, F2, F3, F2, F4 and all these pairs. Very good. So it's just F1, F2. F5, F4? Yeah, so it's the GCD of all these products. Now among these, which is the, so does F3, F4 divide F1, F2 or does F1, F2 divide F3, F4? So F1, F2 divides all the others because F1 divides all the others and F2 divides all the others except F1. So F1, F2 is the GCD of pairs. And if we look at similarly GCD of 3 by 3 minors, then we get F1, F2, F3. So GCD 3 of A is defined to be GCD of all 3 by 3 minors. And we show that the GCD K of A divides the GCD of K x A y, and by symmetry, because these are invertible, that this is also true. So all we have to do is figure out what is the relation between the entries, the minors of A and the minors of x A y. And I won't do the calculation, it's slightly ugly, but it's conceptually what is happening is that the matrix of the minors of x A y will again be linear, will be expressions like this, but only instead of x and y, you will involve more complicated expressions from the entries matrix x and y. So the same kind of argument will show that the GCD of the k by k minors of A is the same as the GCD of the k by k minors of x A y. So what you get is that F1, F2, F3, so GCD 3, let's call this canonical form. So this is GCD 2. And if you know F1, F1, F2, F1, F2, F3 and so on, you can divide them and get back F1, F2, F3 and so on, right. So Fi can be recovered from this as GCD I of C divided by GCD I minus 1 of C. So what this shows is that these matrices are actually not equivalent to each other, they are pairwise inequivalent. So here's a canonical form for polynomial matrices. So why did we do all this work? This is because the equivalence classes of polynomial matrices will help us solve the similarity problem for ordinary matrices. So let me remind you what the similarity problem was. So we said that A is similar to B, B is x inverse Ax or x A x inverse, doesn't matter, for some invertible matrix X. Okay? So we want to solve this for ordinary matrices, not polynomial matrices. So for polynomial matrices, solving the similarity problem is very hard, and it's a problem on which I have written several papers. So it's something that's part of ongoing research, but we will just solve the similarity problem for ordinary matrices. Okay, so here's a very, very beautiful theorem in linear algebra. See, there's this matrix you've no doubt seen, T times identity minus A. This is what we use to calculate the characteristic polynomial. Right? Its determinant is the characteristic polynomial. Now this is a matrix whose entries are polynomials. So the theorem is this: A is equivalent to B if and only if T times, not A is similar to B if and only if Ti minus A is equivalent to Ti minus B. So this gives us a strategy for determining whether two matrices are similar or not. What do? You compute Ti minus A, then you find its Smith normal form, for which we have an algorithm, and you compute Ti minus B and calculate its Smith normal form, and then you check if these Smith normal forms are the same or not. If they are the same, then you say yes, these matrices are similar. If they are different, you say no, they are not similar. Problem solved decisively. So let's try to understand this theorem. One part of this theorem is quite easy. Suppose A is similar to B. Okay, so A is similar to B means that B is equal to X A X inverse. So let me just so I'm proving this part. If A is similar to B, then B is this. Then I can write Ti minus B is X times Ti minus A X inverse. Right, and this X is a constant matrix, of course. In this definition, we are talking about constant matrices. This side, we are talking about polynomial matrices. This X is a constant matrix, but a constant matrix is a polynomial matrix. So this is not a difficulty. So what we get is that you can take Y to be X inverse, and so this implies that Ti minus A is equivalent to Ti minus B. No problems here. It's just because similarity is a much stronger condition than equivalence. You are asking that this Y be the same as X inverse. Okay, so this is not a problem. This is the difficult part. This is the difficult part because what we now know is that Ti minus B is X Ti minus A Y, where X and Y are polynomial matrices whose determinants are constant, of course. They are invertible but they are polynomial matrices. Not only are they polynomial matrices, they are also different. I mean, Y is not X inverse. So there are several problems here. You can't go back so easily. So this is the non-trivial thing, and let's just see how to prove this. This involves a clever trick, and this clever trick is basically a Euclidean algorithm for polynomial matrices, so a division algorithm. Let me explain this. So I'll just rewrite this slightly differently. Suppose P times Ti minus A is equal to Ti minus B times Q. So this earlier I had written Ti minus B is X Ti minus A times Y, but I want to write it in the slightly different form. So you can just take Q to be Y inverse and P to be X. It's the same thing. Okay, and we are assuming that this P and Q are polynomial matrices and they are invertible. Okay, we want to show that A is similar to B. So what you do is you write, I claim that I can write P as, this is some sort of division algorithm, Ti minus B times P prime plus G, where G is a constant matrix. See, part of the problem here is I need to find constant matrices. For proving the similarity, these have to be constant matrices. There is no T in this similarity problem. So where G is a constant matrix. Look, if these capital letters were all just not matrices but ordinary numbers, then this would not be a problem. We have a linear polynomial and we have another polynomial, and we are doing the division algorithm. The remainder should have degree less than this, so it should be a constant polynomial. But the only slight difficulty is that now these things are matrices. So, can we still do the same thing with matrices? And the answer is yes, yes we can. What you do is okay, so P is a polynomial, so you can write it as P0 plus P1t plus P2t squared. The only difference is that now this P0, P1 they are matrices. Okay, like my matrix I had written down 1 plus x, 1 plus t minus t, t. This can be written as 1 0 0 1 plus t times 1 minus 1 1 minus 1, right. So you can just write any polynomial matrix as a polynomial with matrix coefficients and going up to some p n t power n. And I want to somehow divide by this. The idea is similar. You try to use long division. So you take t I minus b, and what should I multiply it by to cancel out the leading term? I'll take p n t to the power n minus 1. So this is equal to, now I got the leading term, but I have introduced some mistake, this minus b p n t. So I must add that again. And then there is p n minus 1, t to the n minus 1 plus lower order terms all the way down to p0. So what I have done is I have somehow taken care of this piece, and now I have to work with this piece. And now I do the same kind of thing, or you can use induction if you like. And at the next stage I will look at t I minus b. Now I have already taken p and t. Here what should I do? I must take this thing times t to the power n minus 2. So p n t to the n minus 1 plus b p n plus p to the n minus 1 t to the n minus 2. And now the error that has been introduced will be of degree will be n minus 2. So you keep pushing it down, and in the end you will end up with a constant remainder. You will have larger and larger expressions here, ti minus b times some polynomial of degree n minus 1, and the final remainder will just be constant polynomial. Try it out in some example. It's just like long division. So this can be done where g is constant. Right. So and this I can do a similar thing with q. I can write q in the form, it's slightly different. I'll do it on the right, q prime ti minus a plus h. So here I had written it on the left, and there I had written on the right, because with matrices this makes a difference left and right. But you'll have to do a similar thing, only thing you'll have to modify this a bit. But we can also write like this for constant matrix H. So we've at least managed to extract some constant matrices. Now let's rewrite this identity using this and that. So what we get is P is t minus ib, ti minus b, p prime plus g times ti minus a is equal to ti minus b times q, which we have rewritten as q prime ti minus a plus h. And now if you try to simplify this, you see you've got this ti minus b times something times ti minus a on both sides. So let's bring those to the left hand side. So what you get is ti minus b times p prime minus q prime times ti minus a on the left hand side, and let's bring the remaining stuff to the right hand side, is equal to g times ti minus a, I guess with a minus sign, plus ti minus b times h. Now there's let's look at these two sides. What's the maximum degree of any entry here? Remember, G and H are constant matrices. So this any entry here, A is also a constant matrix, B is also a constant matrix. So when you expand this out and write down the final matrix, every entry here will be degree at most 1. Okay? But let's look at here. Suppose p prime minus q prime has at least one non-zero entry. Then definitely there will be an entry here of degree 2, because you will have a t here and a t here. So here you have entries of degree 2 unless it is fully 0, but here all the entries are 1. So the only possibility is that both sides are actually 0, that means p prime is equal to q prime. So what we get is that this fellow is equal to 0, which we can somewhat more fashionably write as this is equal to this, and forget about all this. So what we get is g times ti minus a is ti minus b times h. So what you get is gt minus a is ht minus b. But two polynomials are equal if and only if the coefficient constant terms are equal, bh, and the coefficients of t are equal. Huh? GA, yeah, good, I want this. So what we get is G is equal to H. So I can write G is equal to H and GA is equal to BH. So which means that BG, which is the same as GA G inverse is equal to B if we can show that G is non-singular. Okay, the non-singularity of G I am going to the non-singularity of G should come from the non-singularity of P. So what we want to show is that the determinant of G is non-zero. So what we have is, let's say P is non-singular, so P has an inverse. So let's see what the inverse of, okay, so P has an inverse, let's call that inverse S. So suppose SP equals identity. Then we can also write S as Ti minus b times S prime plus some other symbol I want, let's say k, and k is a constant matrix just by the same trick. Then if you use this SP equals I, what you get is that this times this is identity, and so what you get is Ti minus b p prime Ti minus maybe or maybe we should say it like this, identity minus gk. So the product of this, okay, so let me just write it down. So SP, right? So this times this, I was doing it slightly wrong, so I get Ti minus b S prime Ti minus b p prime. Then there's cross terms plus Ti minus b p prime k plus sorry, not p prime k, right? It's k times p prime plus S prime g plus gk is equal to identity. And does this
Prime times k.
huh?
It should be p prime times k.
P prime, no, it's S times p, so SP is equal to I. So hey, one has to stick to one of the conventions. And so what this shows is that so you can also write this as identity minus gk, bring the thing here, is this stuff. Now this is a constant matrix because g and k are constant matrices, so this must also be a constant matrix. So okay, but now we'll do the same degree trick. The degree of this side is at least 2 and this is constant. So the only way they can be equal is if both sides are 0. So that means that gk is identity. So g and k are also invertible. In particular, what we are interested in that g is invertible. So this implies this because g is invertible, and so the matrices are similar. So this actually now fully solves our problem last time of solving the. It's not a canonical form in the same sense that we had a canonical form last time. It's a canonical form in a different world. It's in the world of polynomial matrices, but it somehow solves our original problem of similarity. A little more work can be used to show that this canonical form is actually equivalent to what is called the rational canonical form. So, but that will take a little more time than we have, and maybe I'll stop now. But let me give you a reference to a beautiful book I just learned about a few days ago. It's called Matrices. And it's due to it's written by Denis Serre, and there's a copy in our library. Oh, but I couldn't find it yesterday, so I don't know. Somebody's taken it out. Anyway, with this I'll stop. We'll have some problems for discussion in the afternoon. Thanks.